So
Hello.
for me, it's actually good afternoon. We're about to end the day here. So,
Yeah,
but
super. Thank you.
welcome to Sweden.
Yeah, thank you. But we have snow in Chile, so I don't know if this one imagine Sweden as a snowy country, but apparently it climate change is changing things a bit. So thanks a lot, David. And if you want to share your screen, I think you should be able to do that.
Yeah, before I start,
Sure.
because you asked me to give a talk, and you told me,
Yeah.
can you talk about Arduino and education? So I have like many ways of talking about it. So, so I wonder because I see some familiar faces from the workshop last summer in Trieste. So I would probably avoid repeating the same talk I did in Trieste, unless you tell me that's exactly what you want.
Sure. No. Completely with you. We have about 118 participants now in the chat. So yeah, just a small subset was interested for that workshop.
Okay,
So,
but
but
okay, I will start with something else, and because there is time, if I see there is a stronger interest in more like the pedagogical models and stuff, which is kind of my research, then I can go back to that, and um, and so I will make like an introductory thing that talks about education, but more looking at cases. I think
super.
it's easier to digest on a video call. Okay. So first of all, hello everybody. My name is David Cuartielles. I'm one of the co-founders of Arduino, and I'm a teacher or lecturer at Malmo University in Sweden, and head of the Interaction Design Masters at Malmo University, as well as the head of the new it's so-called Full Stack Lab, which is a lab integrating both engineering and design, looking at the new challenges of creating devices and services for people. So I'm gonna talk a bit about the making of Arduino and Arduino in relation to education. So I'm gonna just like start my presentation here, go, and then I will share my screen and go. Wait, wait. So yeah, so first of all, yeah, how are you? So I like to show this image, which I find quite funny. Um, this is a remain of a building where famous indie musician painted this. I don't know if it's a frog or a monster or exactly what it is. At the University of Austin in Texas, and it's a quite infamous university currently for different reasons. One is because they're removing the laws about diversity and equality because of the Supreme Court in Texas that it doesn't allow to apply any kind of positive discrimination in education, which I think is bad, but also because they are using pretty inadequate measurements to uh, remove the pro-Palestina or anti-genocide demonstrants currently. So, but anyway, I'm showing this because I lived there for the previous 6 months in the previous semester, and I worked there as a teacher in interaction design, which is what I do besides working at Arduino. I just want to give you this picture of myself as a person that works both at Malmo University and at Arduino. So I'm one of the co-founders of Arduino, and therefore I will talk a bit about Arduino in education, and I will present it a bit as a journey into STEAM, which if you don't know exactly what the acronym means, I will come to that later. And of course, feel free to prepare questions for later. But if you really have an urge to interrupt me at any time, just raise your hand, and I'm pretty sure we can look into it. So a bit about myself. So I've been teaching at Malmo University for 25 years. I'm very committed to making education on complex topics as simple as possible and allow people access complex subjects such as embedded electronics, for example. What you see here is my bicycle, and I show it because during the pandemic, we asked in Sweden, we asked all of our students to work in smaller groups and remotely, so the school was closed. So what I did is I prepare portable laboratories that I will prepare in paper bags, and I will deliver them to the students as if you were delivering food. So when students needed materials, I will jump on my bike and I will cycle to the other corner of the city, and I will bring small kits with components for them to work. So this is a kind of like a sticker that I prepared for the beginning of the class when I told my students, meet your trusted teacher, dealer, at a certain square in the city. And many students have never seen me, so that's why I prepared this kind of thing so they could see I was the guy looking strange on a blue bicycle on a square. So in Sweden, we didn't have to wear masks. We could go to public spaces, sorry, but we couldn't work in public buildings. So it was kind of like a weird situation. But this is my level of commitment to education, right? So I think it's very important, and I think it's important to be accessible to students. And sometimes it requires special measures, like in this particular case. So more about myself, I wrote a doctoral thesis about the design of platforms, where Arduino is just one of the platforms I studied. And so that's kind of like the research that I conduct. I look at platforms, and looking at TinyML, for example, as a platform is very interesting. What a platform is something that could be discussed. So if you're interested in reading this, it's open source and Creative Commons, so you can download it from the Swedish database of doctoral thesis. But I don't recommend it. It's very long and heavy, 350 pages long. So yeah, but it kind of covers the idea of what it means for people to really have access to things, like platforms. I mean, that would allow and empower them, would allow them doing things in different ways. But my main focus is interaction design. And interaction design is a discipline that is taught since 25 years ago at Malmo University. It looks at the interaction between humans, non-humans, and digital artifacts, which is products and services. So this is the context that I want to build for you to understand why Arduino is born. Um, because yeah, it emerges because of a need to have systems for people to learn about digital technology. In my everyday work, I do things such as what you see here. So this is a multiple test of many platforms in parallel, where I am testing the performance of different single board computers. And there you can see an Octodroid, a Raspberry Pi, and a Banana Pi. And I'm checking which one of them performs better. As you know, a single board computer is more than just a fast processor. It has to interact with memory, has to interact with storage. So checking the performance of a system is much more complex than just the amount of megaflops a processor can provide you with. So you have to look at other things. So I use standardized measurement tools to look at how different systems running the same version of Linux, which in this case was Dev1, which is like a minimal version of Debian, could run and operate in order to proceed with blockchain-based operations. I just want to say that the Banana Pi gets so hot that I have to have a fan here. So this thing on the bottom right that you see here is a real fan, like a home fan. So I needed to provide the board with a lot of fresh air for it not to catch fire. But at the end of the day, many times what I look at is how people interact with machines. And I do things like what you see in this picture here, which I did in 2011. This is a system where we both could program interactions using graphical elements from like, like buttons, sliders on the screen or whatever, with physical elements. So we combined a whole framework for programming in Android, and on the other hand, a framework to program in embedded and have them to communicate via Bluetooth. So in here, we were some of the first people in the world to ever do this connection between Android phones and physical devices. And it was a very prototypical kind of thing that we used in several workshops to learn about how to use these technologies together. The idea was to figure out prototyping kits so people could imagine future devices where screens will be involved. And back then, having access to cheap screens was very hard. So it was actually easier to get mobile phones that had connectivity and everything than getting like a simple multicolor OLED screen with enough resolution. Nowadays, things have changed completely. So access to parts is much easier, actually. So the thing is that people use platforms to learn and create things. This is the, in a nutshell, what really matters to me, what I look into very much. And in that context, I want to show you what I produce as the first. This, you could call this one of the Arduino grandfathers. Okay, so at Malmo University, I was hired to teach programming, which means I was, after graduating from the engineering school, I went to Sweden and I started teaching Java to design and art students at Malmo University. So that's quite a challenge. And so I was at some point I was very inspired by some publications about ubiquitous computing, and I decided that I had to teach embedded technology to students. It was 2003. So I approached my colleagues at the university and I suggested using this self-made platform to teach my students about electronics. And I remind you, these were design and art students. I didn't have any kind of like strong science background from high school. Okay? And I was teaching at the bachelor's in the first place. So students will build their first computer that will look like this on the front. In this big empty socket, there will be a microcontroller. Unfortunately, I don't have any pictures with this board with microcontroller on it. And on the other side, you will see this mess of wires. The students had to build this board from scratch. So part of the idea of teaching technology for me included teaching all of the nitty gritty details and building things from the bottom up. So students had to learn electronics through the craft of electronics. So you have to build a circuit to understand that the current goes through the wires, that it goes through circuits, that things happen inside those circuits, and that they can take inputs and they can produce signals that go to outputs and so on and so forth. So students will build these systems and they will build things with them. So I would, for example, give them the task of trying to figure out which things to automate in everyday life. So they will go out in society and study everyday routines from people and try to figure out which kind of things to do. And sometimes they will do very crazy things. For example, one of the first projects I ever made was this, which is an automatic confession booth. So if you if you're a Catholic like I am and you go to the church, then you know how confession works. You basically go into a place where you don't really get to see the priest and you confess your sins, and the priest gives you the absolution through a certain punishment. So this was a robotic kind of box made in 2004 that would interact with you. So it had sensors in places like I'm gonna actually annotate this image so you can see this. Oh, this Zoom doesn't have annotation. Okay, so forget about what I just said. I will not annotate it, but you can see that this box, which is a confession booth, had sensors on the lock, which is a metal lock that is there. It had sensors on the pillow that is on the floor, and it had a microphone hidden underneath this this tiny can that is on top of the shelf. And so you will enter the booth and you will hear a voice telling you, brother, would you mind closing the door? You will close the door. What's it? Brother, would you mind kneeling down? You will kneel down. And they will tell you to confess your sins and you will go telling your sins, right? And then at some point you will hear a voice that will go like, uh-huh, mm-hmm, uh-huh. So this whole thing was done with um, one of these boards that you saw before. So one of these. And an old CD player, a bit like what you see in the following image, like this. You see on this picture on the right, you see an old CD player that could play MP3 files. So you had hundreds of sound loops that you could pre-produce. So you had tens of variations of, would you mind closing the door? Can you close the door? Close the door. So by randomizing these different sentences that said the same thing, you will give people the impression that there was somebody with a microphone, but the machine was completely automated. In this other picture, what you see is another very similar system, but instead of having sensors on the door, it has a presence sensor and a weight sensor. So it detects whether there is somebody around the chair or somebody sitting on the chair. And this chair had this was representing this character that was first inviting you to sit on the chair. It will tell you, "Oh, I'm really lonely. Would you like to sit on me?" And then once you sit on the chair, it will tell you, "I think you're really heavy. Would you mind leaving me?" So you had this chair that had this kind of like duality characteristic that was inviting you to come and then to go and was very uncertain and so on. And it was, for many people thought that there was somebody hidden with a microphone talking to them, but everything was completely automated again, right? So we asked students to really make machines that would evoke feelings in people, that would make them believe that the machines were somehow alive. And for that, we use this self-made technology. Well, this very stupid kind of machine that is done to really entertain some conceptual ideas is the grandfather of Arduino. Mhm. Yeah, as I say in the chat, is sentient machine. Yeah, in a sense, yeah. So the idea is to really have a machine that can give you the impression that they feel things, that they respond to you with like some sort of consciousness. But everything was very random. So, but it could really build some sort of like a conversation. So, but how replicable is this? You know, how many of you would go and take a breakout board and start wearing the breakout board from the back and try to make your class like this? I when I just entered the call, Marco was showing you this beautiful notebook with all of these explanations how to do these very complex operations around TinyML, right? Um, that is a very replicable format. If you have the tools at hand, you know, it has like step-by-step instructions, has very good explanations and so on. So how replicable do you think it is to do something like what I was showing here to you? It's obviously, yeah, exactly. As you're saying on the chat, it is not easy, right, to replicate. So that's why we had this idea of building the board one step beyond the protoboard. So this was the first design for Arduino that was made in 2005. And as you see, it was made by Padre Massimo and myself. And what we did here was to offer a PCB, a printed circuit board, where you only had to solder the components. So the previous prototype would take maybe 10 or 15 hours to build, depending on your skill. This will take 3 hours to build. And as you were building it, I will be telling you as a teacher, well, this is a resistor, it behaves this way. This is an LED, it behaves this way. So students will learn about how components work and slowly build this board towards something that functions. And then we will burn the bootloader on it and explain, well, this is a bootloader, and this allows the board to communicate with a computer and load new programs on it. So this was really a big success. And very quickly, we went from 0 boards to a couple of thousand boards made. And people really liked it. And teachers from all over the world started to ask for more boards because they wanted to run more classes and so on. But there was still a bit of a barrier to jump over because you had to find the components and you only got the blue board and some people really wanted this off the box out of the box experience. But what could you do with this board? Well, you could do things like what I'm going to show you now. And so first of all, I want to just give you some brief explanation. I'm in my master's in electronics. I took a class in medical electronics. So I experimented with electroshocks on the body as part of my master's. So I do have this experience. So if you don't have the experience, please make sure if you want to replicate what you're going to see now that you learn about it first. Okay. So, but the first project ever made with an Arduino board was this thing you're going to see here now. It's called the involuntary dance machine. And it consists in a machine that can play a song. And as you play the song, it cuts the sound spectrum in 4 parts. And depending on whether the signal goes over a threshold in one of those 4 parts, it will electroshock an elbow or a knee of a person. So we have a dancer that is hanging from the ceiling with a harness, and based on the music, it will be electroshock and dance to the music. Okay, you can find this movie on YouTube, by the way. So this is completely in the open, but it was made by my students in 2005. The one thing that I think is important for you to know also is that it's very noisy. So you only hear the music in the back. So if you don't wear headphones, you will probably not hear the music. You will only hear people laughing because it's a kind of a hilarious prototype.
Okay, so we have loud music outside, so you can see it here. It won't be that loud because we don't have a PA. So, but now we'll kick it.
Well, you see, you get the idea, right? So it's I mean, the whole idea of this project is that the students had to look at ways to take control of the human body. So the idea was more to think about building some sort of like exoskeletons or other machines that would like somehow direct you into different things. But these students had the idea of like directly controlling the body through electroshocks. And it's interesting because actually electroshocks are used a lot in medical electronics to, for example, help people with like small disabilities in their walking, where you have sensors in your shoes and then you give a small electroshock under the knee, and that helps the foot to like tilt upwards, so it which gives a very natural kind of walking for people that have issues with their muscles. At the same time, you can use for evil, like in this particular project, which is a little bit crazy, right? But I have to say this was very successful because it really allowed people to see a very direct connection between the music and the control, which was the intention for these design students. Anyway, like talking about more technical things, this is the first robot ever made with Arduino. And I mean, talking to this very technical crowd, I think it's interesting for various reasons. As you know, the first smartphone was made in 2007 by Apple. So this robot is actually controlled from a device, which is a pre-smartphone device, which is I think it's a Dell handheld device that has a touchscreen and can be programmed in Flash. So one thing I'm constantly looking at is how new technologies, new softwares, new communication mechanisms, new platforms, new protocols can be used, mesh with one another to do different things. This particular example, what we see here is how a robot that has an Arduino board on the front is controlled via Bluetooth. Just to give you more context, in 2005, Bluetooth was just reaching the market. It had existed since before, but at that time was just barely reaching the market, and it was really hard for us in Europe to get access to Bluetooth chips. In this case, what we have here is a mechatronics students from China that got one of our boards in order to control this one robot, which is a multi-pit robot from a Japanese brand called Gaken. And he controls it with Bluetooth. So let's take a look at the video on how this works. As you can see, it's quite impressive to see how this moves. But as I said, to me, the most important thing is that this was the first project ever made with an Arduino board by somebody I have never met in my life. So up to this point, everybody, this is 2005 still, everybody that had made projects with Arduino were either my students or some of my partner students. But at this point, we start to see how the boards were reaching other people, and they were being used mostly in educational and research projects at universities and schools. But then Arduino has been used for many other things. For example, during the pandemic, this is an example of how an Arduino board was used on a ventilator that made it in Spain to actually clinical testing. So this device controlled with Arduino could eventually be used in medical emergencies. Or, yeah, the big question is, what is Arduino for many people? So for many people, Arduino is actually this blue board. It's a board with an 8-bit microcontroller that can do a lot of things. As a computer without a screen or a keyboard, it requires a software to program it. But Arduino has evolved over time, and there is some newer versions of it. So this is like the latest of the Arduino Uno boards. On the left, you see the minimal edition of it. On the right hand, you see the Wi-Fi board that besides just having the processor, which is in this case is a 32-bit Cortex M4, it also has an ESP chip that has Bluetooth and Wi-Fi capabilities. So Arduino has adapted over time to offer state-of-the-art technology to both the beginner but also the professional. But as I said,
available on revision 4 Wi-Fi microcontroller. The first one is the
one second,
built-in
I will turn off the
LED
sound.
matrix.
So this is actually the unboxing experience from one of our Arduino community members that takes this board out of the box and is going to plug it for the first time. So one thing we really take care at Arduino is in making sure that the experience works in every sense of the word. And by working, sometimes we also mean that it has to feel good. And in this context of feeling good, this particular board, when you turn it on, it makes a very nice animation. And in case you haven't seen it, you're going to see it now. So if you develop a board with a screen, the least you can do is to just have a cute animation when it boots. But again, Arduino boards are boards that run software that has to be programmed somewhere. And to program them, we created the Arduino software that was originally based on the processing project. And processing is a software that is currently still used to teach people how to program. The processing IDE is programmed in Java. But as you know, Java is slowly being discontinued from the operating systems and is going back from being offering like a very safe user interface to basically sit in the cloud and work with security. So if you want to have a software that people are going to use in modern computers, you need to migrate most likely to other programming environments. And in our case, we chose to use an Eclipse project in order to develop the new Arduino software that is entirely made in TypeScript, as you see here. Arduino software 2.x, it actually has the debugging capabilities for most of the newer boards, among other things. It has code completion and so on. So it's more of a modern IDE, but it's super simplified. So if you feel comfortable with more advanced professional softwares, you might find Arduino software a bit too simple. But it's definitely a great tool when you're starting or when you're learning, or if you really know all of the nitty-gritty details of your projects. It's a very simple way to get things done very quickly in a system that just works. It doesn't require much to install in order to just make it function. And Arduino software is downloaded many times per day. It's actually downloaded once every 2.5 seconds, which is a tremendous amount of downloads. So also, something at Arduino is that we have all of our documentation for free and openly available under Creative Commons licenses on the Arduino website. Again, you're welcome to take this documentation, translate it to other languages, use it in your courses, make books with it, augment it. You can also contribute because currently all of our documentation is contained in a GitHub repository and is then rendered by a Python script. So what you see here is an example of different views of the Arduino documentation side that is all rendered from plain text. So it's it gives you like a more pleasant navigation experience. But if you feel like you want to nerd around, you can always just go to our official documentation GitHub repository and read things directly there as plain text. From that perspective, you can also contribute making your own articles and proposing new things. We're quite picky when it comes to proposals of new articles from the perspective that it needs to be properly written. The examples need to be like clear, and they have to include a minimal amount of parts so that it's easy for people to replicate them. Remember, this is like the vanilla examples for the documentation of Arduino. So the Arduino website, it gets visited about 60 million times per year. So it's quite an amazing amount of people using the documentation here on a yearly basis. So it's very important for us that everything works in a rock solid way and that we avoid as much as possible kind of like any kind of security threats. And that's the reason why we chose to use GitHub as a platform for hosting the content, and then we render as HTML so that we avoid any kind of like problems with it. In the past, we used to have a wiki structure and so on, but there's a lot. While it's easier to have people to contribute to it, it's much harder to keep security in the system. So what is the key aspect of this? Well, when it comes to education, all of Arduino blocks are open. In other parts, let's say the Arduino professional line, you get access to all of the documentation once you enter into more or a project mode. Like you get all of the basic documentation for sure, but if you want to make your own boards based on our boards, you need to really establish some sort of a collaboration with Arduino. It could be a research collaboration from a university, it could be different things, okay? It doesn't need to be a commercial collaboration, but it's just want to make it clear. We try to minimize the amount of times we're copied, which happens quite often. So anyway, we came to talk about education and pedagogical models and different ways to approach technical materials in class, mixing technologies with other materials, reaching as many people as possible, but also thinking about the limitations of technology, because technology gives a lot of opportunities, but also limitations. For example, when you teach the same class again and again for 20 years, like is my case, you start to find that people tend to repeat the same examples over and over again, you know? So once you invent a way to use tools, the tools themselves, they kind of transmit their use to people, and then people very quickly start using them in the same way all the time. And while digital technology allows you to do many things, when you give an Arduino Uno to students, they always want to make a robot or a water sensor for plants, or, you know, it's very hard to find new and innovative uses all the time. So we also observe that the same way we teach, or what we were teaching for many years, other students, or so other teachers decided also to work in a similar way. And we all fall under the umbrella of STEAM. And as you know, STEAM stands for science, technology, engineering, arts, and math. Okay, so this in the beginning, when people talk about STEM, which did include the arts perspective, the more humanities perspective on the use of technology. But we at Malmo University prefer to look at STEAM, and many other places in the world are also looking at STEAM. So we use art as a way to bring a critical perspective on the use of technology and think about the real use of it and whether it will affect people or the environment. So the ethics are part of this as well. So I'm going to talk about a couple of projects that have to do with this. So the first project I'm showing you here is done at the Computer Clubhouse Village, which is a laboratory network that was made by Intel in collaboration with MIT Media Lab many years ago. And this project was running for many years, financed a whole bunch of computer rooms all over the world, and they gave money to buy equipment and to hire 2 lab responsibles to run the place for some years. And the idea was that the community receiving this investment would then figure out ways to continue working with it. Well, I arrived to Mexico City in 2008, and I started collaborating with the existing Computer Clubhouse Village that had been there for some years, but that was a bit in disarray. And I helped rebuilding it by designing a robot for them to use with their kids, revamping the whole computer room, looking for the use of free software in the computers, and so on. And in response, the students started to build things such as this, which is a Pac-Man robot, where they combined paper mache, which is a specialty of Fare de Oriente, which is a center in Mexico City where I was working for 4 years, with electronics. The design that I made was this robot, which is based on the Arduino Uno board. And the idea was that I enlarged the PCB to include the possibility of attaching some motors to it, a battery. We use a table tennis ball as a back wheel. And you can't really see the front part of the robot, but the front part of the robot includes a bunch of sensors. So this was the first Arduino robot I designed that was completely designed from the original hardware designs of the Arduino Uno, basically just enlarging the surface of the board and adding the components in a different way, adding a motor controller, and so on. So this made this thing automatically programmable using Arduino Uno. And I could just use the extra libraries that I created for the students to use these robots in different ways. And then again, they will do things such as this, which is like another version of the robot that is supposed to go around and then make a small dance. So we have plenty of videos of activities done with this robot over the course of 3 years. So you can imagine which is the impact that making this open source design can have in education, so that hundreds of kids year after year can use this modified version of the design. As a consequence to that robot, I realized that it was very important when designing educational robots that there was a component that should be easy to replace, so that the kids could have a trustworthy piece of technology, and then on top of that, they could play with crafts to build their own things. So in this particular case, I designed this robot to be made with cardboard pieces. So everything that goes on top of the electronic circuit and the motor controller and so on is made of cardboard pieces. And we will provide them with like basic pieces that they could paint and cut, and they could destroy them in whatever way they wanted. And at the end of the workshop that would last for a week, they could reuse all of the parts by separating the craft components from the original electronics. Then the kids would do things such as a Garfield cat with 4 eyes, or multiple insects with different capabilities, So they would modify them and paint them, and they would make competitions and fight each other and whatnot. Funny enough, the cost of these robots was very similar to the previous one you saw, but there is a 5 years time difference between the original design and this one here. So you can see how also the advancement in educational technologies also makes the access easier, right? So inspired by that, then I started to look at how it would be possible to create content materials for a full class in formal education. Until here, I had been looking at extracurricular activities, but in 2012, I got the possibility of creating a full educational program for the region of Castilla-La Mancha in Spain, that included enough materials to run 26 different experiments. So not all of the students in the class will do the same kind of experiment. So week after week, the students will advance in knowledge, in working in groups, and each one of the groups will get different experiments to do. So we could like kind of orchestrate the learning, and they will learn similar things, but not exactly the same, and they will pitch their learning to their colleagues. And so we have this circle of research, building, explaining, and then repeat week after week after week for 4 weeks. And at the end of that period, the students will get to decide on how to make their own project. And then they will brainstorm, and they will go through a full design process and spend 4 weeks building a final project. So this kit that you see here included all of the parts needed to repeat this project in the school year after year. And so we started in Castilla-La Mancha, but we slowly expanded through different regions of Spain. In the end, we had reached over 2,000 schools all over the geography of Spain, but also we reached after-school programs, for example, in Ecuador, United States, or Denmark, just to mention some random places. And this kind of kit as a concept had a value for quite some time, and it worked really, really well with the whole design of activities and so on. But then we started to suffer this kind of like, it's very classic, right? Like when people are starting to understand how it works and they want to make their own kit, and they start to look for their own parts because it's typically cheaper to find parts from other sources, and then it will be really hard to, you know, sustain over time. You know, and in particular, this kind of kit was paid fully by foundations, so the schools didn't have to pay anything. But at the same time, it was really hard to keep it alive without the support from those foundations because it requires so much work just to, you know, maintain the software, maintain the parts, make improvements on parts so that the students would like include the improvements there of the learnings from the previous year in the following year, and so on and so forth. And I think this is a recurrent problem with technology and STEAM in general, that we don't have set curriculums across the world, so we don't know exactly what people are going to learn, which is also good because it allows us to innovate. But at the same time, it makes it very hard to design these more complex systems that will provide a better learning experience. But okay, we can talk about that if you want to in the Q&A. But which kind of things you could do with this kit? Well, we had some projects that were kind of funny. For example, instead of having a 4-leg robot, we had 2 clowns carrying a trolley. And it's still a 4-leg robot, and it's controlled by Arduino, but it's and with 2 servos, but it has a different shape, you know. And this is an example on how the documentation would look like for the school. So they would like get projects divided in blocks. Each block represents 1 or 2 weeks of work. And with the project here, it's called the binary LP. They will learn about binary counting by building this small long play player. And they will use a line following sensor from a robot in order to detect the shadows on this disk. Okay. You see, the documentation would include everything about the materials, and then step-by-step instruction on how to mount it, and so on. So this, just to give you some idea on chronology, this project was made before Arduino's documentation site that I showed you earlier. As a matter of fact, the design of this website influenced very much how the official Arduino documentation site would be in the long run. So we will incorporate a lot of the learnings that we had working with educational projects to design the full system for all of the Arduino community. This is another video. In this case, what you're going to see here is the outcome of one of these educational projects in a region. In this case, it's in Catalonia in Spain. And here we work with 175 schools, and all of the schools got the chance to send their class to present the final projects at the museum. So here we have about 4,000 students coming together to show the outcomes of their Arduino projects after 4 weeks of work. So you see the variety of plays is huge. So there was in this, something important for this fair, that there was no constraints in the kind of projects the students could make. So they would make like small printers, they would make just software projects, they would make like this project, for example, I like it very much. It's about finding books in your bookshelf. So with a laser pointer, it will point to the bookshelf and tell you where the different books are based on a database. Or there will be like very low key projects, like this one, for example, is a small keyboard made with recycled soda cans, so you can touch and play music. And this is a project that was voted like the best project in the whole fair, which is a bubble blowing machine where the students didn't know how to use a relay. So they invented one by using a servo motor. So as you see here, there is very like more traditional projects like, doing sumo robots, and there is very creative ones like bubble blowing machines. So that's a very important aspect for me, for the teachers that participate in this initiative, that they were not constrained by using the classic kits where they just have to make one robot that does one thing all the time. Uh, Having this open-endedness was key for the students to be inspired and try things that were interesting to them. And also, it was very important that in these presentations, we didn't have any kind of like prizes, for winners or anything. So all the schools would get a small present, like you see here, and the students would vote. Oh, sorry, yeah, vote for the best project in their eyes by putting a small sticker in the other projects like announcement board. So at the end, what you will get home is an announcement board covered with stickers that said that people like your project somehow. So you get appreciation from the others, and there was no grades when it comes to this. But then at Arduino, we've worked with other things as well. So sometimes we work with European research projects. In this particular case, what you see here is a project called Pillars that we made together with University of Malmo in Sweden, the Copenhagen Institute of Interaction Design, and some other universities like UCL in London and so on. And this particular project, we created a system that would recognize how the students were collaborating with one another. Students were monitored with a camera that would look at their eyes. So we could see whether students were looking at the projects or they were looking at one another. And so we would be able of evaluating the amount of communication happening. But also we invented this new system we call SLOF, which is Arduino boards that you can hot plug on one another, and then they appear on the computer screen, and you can draw different relationships between the boards. So we could monitor exactly which boards they were using and how they were using it. And with that, we could feed an AI that will help us understand in advance whether a project was going to be needing help from teachers or not. So it sounds a bit science fiction, but it's all pretty straightforward. So what I'm going to show you here is a prototype of our project, SLOF, which is allowing you, as I said, to connect different boards together. And when you hot plug them to one another, they show up on the computer screen, and they allow you to the software that we created allows you to program them by building connections between them. So the moment you add a sensor to the computer, it shows up on the screen. And when you interact with the sensor, it shows the results on the screen. If you add more boards to the computer, they will also show up on the screen, and then you can make them relate to one another by connecting them with these virtual wires. So in this way, you can build your own simple systems in no time. So we manufactured 99 of these systems, and we use them in research projects, by doing tests with different schools and universities. And we gave students a task of designing and building things in 1 hour. And it was typically like very easy for them to build anything they wanted in just 1 hour. So they did all of the crafting, connected things, they saw how to plug things together, and they had an interactive device built in 1 hour. Something that would have taken several hours, when not days before, using just normal programming and components and breadboards. So you will wonder, why wouldn't we then just do something like this and manufacture and sell it? Turns out that these kind of systems, they end up being quite expensive because of the amount of parts they need to have integrated in them. So on other things, I have also been analyzing, for example, the work of the foundation called Ibercivis in Spain, which is a citizen science foundation that's looking at many different activities, among others, more classic like space activities like CANSAT projects and so on. So they organize the yearly national CANSAT competition for Spain, where students from all over Spain propose projects, and 10 of the schools are selected to come together for a week and work in building their own small CANSATs that are shot in the sky with rockets. The students build everything. They build the satellites from scratch, and they build the control centers where they capture information from the satellites in real time as they fly on the rocket and as they fly down using a parachute. And students go into the desert. This is a control area by a military from Spain. And you can see the kids coming with their antennas to monitor the launch of the rockets. It's very cute to see them holding the antennas because, as you know, these are Yagi antennas, and